Well, hello, ladies and gentlemen. So we're going to continue on with psychrometrics today. So last time we introduced the concept of moist air, which is a mixture of H2O vapor and dry air. So an ideal gas mixture of dry air and H2O vapor to produce moist air. And of course, moist air is what we're breathing and living in all the time, not perfectly dry, so some kind of moist air. So this is a pretty important topic. So we're going to introduce additional properties today. We're going to introduce the enthalpy of the moist air, H tilde, and the specific volume of the moist air, V tilde. And these have units of kilojoule per kilogram of dry air, not mixture, not moisture, but per kilogram of dry air. So we're going to introduce these properties, these tilde properties, which are on a per kilogram of dry air basis. And then we're going to introduce an extremely useful chart called the psychrometric chart. Psychrometric chart basically takes most of the grunt work out of doing these psychrometric problems that you're going to be introduced to here. So we're going to do an example involving evaluation of properties using the psychrometric chart for some moist air. We're then going to be moving on to dew point temperature. What's the dew point temperature? You've all seen dew out on the grass in the drill field, or dew or condensate dripping off of a cold window or a cold surface in a room. And then we're going to talk about adiabatic saturation. We're going to actually apply an energy balance to a particular situation involving flow through a duct. No heat transfer, so that's why it's called adiabatic saturation. So we're going to talk about a situation involving moist air flowing through a duct adiabatically, and then we add moisture or add water to it to get it saturated. We're going to talk about this particular situation, apply the energy balance, and then introduce the concept of the wet bulb temperature. The wet bulb temperature is a very useful concept that allows you to quickly determine experimentally the physical humidity and relative humidity of moist air. So we're going to introduce this concept of wet bulb temperature. Once we have all these concepts learned today, we'll be able to do fairly serious problems involving heating, ventilation, and air conditioning. And we'll do that in the next lecture, okay? But we got plenty of stuff to do for today. Okay, so moist air properties, moist air properties. So moist air props. And the props we're going to be looking at today are on a per kilogram of dry air basis. So per kilogram of dry air. So we're all used to the properties, specific volume, specific enthalpy, specific internal energy. Those were all energy per kilogram or cubic meter per kilogram in the case of specific volume. So the way we do these psychrometric problems is we're not dealing with on a per kilogram of moist air mixture. We're going to be evaluating and doing all these problems in the future on a per kilogram of dry air basis. If we make it per kilogram of mixture, it's just way too complicated. We're going to do it on a per kilogram of dry air basis. So in our case, H becomes H tilde, and the unit on H tilde is kilojoules in the mixture. And so this is moist air. Kilojoules in the mixture, which is moist air, divided by kilogram dA. What's the dA refer to? It refers to dry air in mixture. Okay, so when you see the tilde over the H, that means kilojoules per kilogram of dry air in the mixture, okay? So instead of per kilogram of mixture, it's per kilogram of dry air in the mixture. So that makes the problems a little bit easier to solve. All we need to do is figure out what the mass flow rate through a duct is, mass flow rate of dry air through a duct, and we can calculate the flow of enthalpy through the duct. So expressing moist air quantities in terms of tilde quantities per kilogram of dry air is actually going to be very useful. We do the same thing with specific volume. So specific volume becomes specific volume tilde, and that becomes cubic meters of mixture. And what I mean by that is moist air divided by the kilograms of dry air in mixture. Okay, so when you see these tilde quantities, think in the denominator per kilogram of dry air. Okay, so that's how we're going to be evaluating properties for most of these problems in the future. Okay, all right, let's move on to the psychometric chart. Let's move on to the psychometric chart. So the previous example that we did, we calculated what? We calculated absolute humidity or the humidity ratio. We calculated some other stuff. We had to use some fairly complicated formulas. We had to look up saturation pressures and tables. It was kind of a pain to do calculations using saturation tables and formulas relating relative and absolute humidity. Well, lucky for you, there is a chart that allows you to quickly and easily relate various properties for moist air systems. And that's called the psychometric chart. So PSY CHROMET metric RIC, psychometric chart. Psychometric chart. So this is a graphic that you can use to evaluate properties for moist air. Moist air at 1 atmosphere. Psychometric chart properties assume, unless stated otherwise, pressure is 1 atmosphere for the mixture. Okay? So how does this work? Well, let's draw some axes here. So the psychometric chart has this inverted axis here, and on this axis, well, I guess maybe it's better to say increasing in this direction and increasing in this direction. On this axis, we have temperature. So temperature T for the mixture. So temperature T, sometimes referred to as dry bulb. We'll talk about dry versus wet bulb in a bit. So the temperature on the x-axis is the temperature of the mixture. The room temperature, the air temperature, whatever it is usually called the dry bulb temperature. It's temperature T. On the y-axis is the humidity ratio or absolute humidity. So here we have omega. Temperature is usually in centigrade, and omega is usually in grams of H2O per gram of dry air. So I'll put DA. DA means dry air. You can do grams or kilograms or whatever. Whatever. You have to look at the unit, on the psychometric chart. Have to look at the unit on the psychometric chart. Okay? Could be kilograms. All right, what else do we have here? Now we have lines of constant relative humidity. So these are lines of constant relative humidity. Okay, so relative humidity is going up as we move across these lines. So maybe this is relative humidity of 100%. Maybe this is relative humidity of, I don't know, let's see, 90, 80, 70%. Okay? So if you want to calculate the absolute humidity or the humidity ratio, let's say you're given a temperature and a relative humidity, and you want to calculate the absolute humidity ratio, all you got to do, so let's say this is your temperature T, and this is your humidity, relative humidity. All you got to do is go to the constant relative humidity line, and there you have omega evaluated at temperature T and a relative humidity. So that's a fairly simple way to get absolute humidity or the humidity ratio using temperature and relative humidity. You could also do the same. You could start off with an absolute humidity and a temperature, and then you find the relative humidity, okay? All you need is two properties because it's a two-dimensional plot. All you need is two properties to determine the state, okay? Now, there's also additional quantities on this plot. It becomes a little bit more complicated here, but we also have lines of constant. Let me make sure I get we also have lines of constant enthalpy tilde or H tilde. So we have lines here. We have lines of constant H tilde. So we have H tilde, lines of constant H tilde that go something like that. And then we also have lines of constant, get some different chalk here, lines of constant V tilde or specific volume. So we also have lines of constant V tilde. They look something like this. They're not quite vertical. I think I'm making that a little bit too vertical. A little bit too vertical. They got more of a slope than that. So we have lines of constant, lines of constant V tilde. So here's V tilde as well, okay? So you give me two properties. You give me a temperature and a relative humidity, let's say. I find the state, and then I can immediately go to the nearest or interpolate to the nearest line of constant H tilde, constant V tilde, and I can get my specific volume for the mixture and the enthalpy for the mixture per kilogram of dry air. Okay? So that's kind of how this plot works. There's some other stuff we can do with this plot, but we'll talk about that a little bit later. So let's actually have a look at this thing. So here we have a psychrometric chart, a little bit hard to see here. Unfortunately, my scanner here is not the best. So what we have here at the top where it says percentage saturation, you can indicate that that refers to relative humidity, percent saturation. Here's 90%, here's 100%. It says saturation, if you see here, this line right here represents 100% relative humidity. So that's the saturation line. 90%, 80%, 70, 60. So this axis up here indicates the relative humidity and the value of the lines, the blue lines here of constant relative humidity. On the y-axis we have here, so we have the humidity ratio. It says here moisture content, kilogram of moisture per kilogram of dry air. That's what it refers to here. Here we have dry bulb temperature. So this is your T. T is on the x-axis. This is your called the dry bulb temperature. And then specific enthalpy. If you look here, it says specific enthalpy. So this is your H tilde, and this is your H tilde. And what you do is, this is at an angle. How do you get the angle right? You line up, so let's say there's a 30 kilojoules per kilogram of dry air. Let me match it up with the 30 right over here. This line right here represents the isoenthalpy or isenthalpic line, H tilde equal to 30 kilojoules per kilogram. So The lines of constant enthalpy, H tilde, go something like this. And you use the axes here in the scales to get the proper value, okay? We're going to do a little example here on how to use the psychometric chart. I think it's not obvious how to use it at this point. So we're going to take a moment here to do an example involving the psychometric chart. So let's get started here. Let's say we have a room. This room contains moist air. The moist air temperature is 20 degrees C and the relative humidity is 80%. By the way, the room is at 1 atmosphere. Depending on the psychometric chart, it should typically be for 1 atmosphere, but there are psychometric charts made for higher elevations or elevations under different pressure conditions, and that modifies slightly the values you get off the psychometric chart for the various properties. Okay, so we have temperature, we have relative humidity, we know we're at 1 atmosphere. What are we supposed to find? I want to find the humidity ratio omega, kilograms of moisture per kilogram of dry air in the mixture, the moist air mixture. I want to know the specific volume of the moist air mixture, and that's going to be in cubic meters per kilogram of dry air. And then I want to look up H tilde, which is going to be kilojoules per kilogram of dry air in the mixture. And then I want to know the temperature. I want to know the temperature such that under this relative humidity and this temperature, I want to know how much I can reduce the temperature in the room until I get a relative humidity of 100%. I want to know how much I can reduce the temperature of the room until the air is as saturated as possible with moisture and can't hold any more. Relative humidity of 100%. We're going to use a psychometric chart for this problem, okay? Okay, let's get started here. So first of all, we're at 20 degrees C and 80% relative humidity. So let's go to our psychometric chart. Let's go to the psychometric chart. So first of all, let's find 20 degrees C. So here's our 20 degrees C right here. Here's 20. So I'm going to draw a line here. I'm going to draw a line here indicating T equals 20 degrees. Okay, so there's my 20. I'm going to reduce the contrast here. This is killing it. Ah, that's better. There we go. That's better. That looks a lot better. Okay, so there's 20 degrees C. My dry bulb temperature or temperature T is 20 degrees C. Now I need to find 80%, 90, 80, 100%. So here's my 80% relative humidity line of constant relative humidity. So I'm going to follow this 80% all the way down until I hit my 20-degree vertical line. And I'm going to put a little dot right there. A big dot, little dot, big dot, whatever. Okay? Now, I'm going to draw a horizontal line as best I can with the intersection of my 20 degrees and my 80% relative humidity here. A little bit hard to see. That looks about right. Just kind of eyeball it here. I'm going to draw a line, a horizontal line. And I intersect on the x-axis with an absolute humidity of 0.002. And the unit here is kilograms of H2O per kilogram of dry air. It can be grams, it can be kilograms, it doesn't matter. So my omega, my absolute humidity, running out of space here, my absolute humidity pulling off the chart is equal to 0.012, and that's going to have units of kilograms of H2O per kilogram of dry air, dA. Okay, I'm going to get rid of this omega here. I don't need this anymore. Okay. In fact, I'm going to get rid of this too, and get rid of this. Now let me put up here on the top of the chart. So 80% 80% relative humidity. A little bit difficult to see. So this is 80% relative humidity, okay? Puts us on this line of constant relative humidity. The intersection with my 20-degree isotherm gives me the absolute humidity, okay? Absolute humidity. I think I can back out a little bit now that the resolution is improved, okay? Okay, so let's write the absolute humidity then. Let's write the absolute humidity. I know what that is. So, analysis. So the absolute humidity is the absolute humidity evaluated at 20 degrees C and a relative humidity of 80%. And I get approximately 0.012 kilograms of H2O per kilogram of dry air. Okay, so I'm going to write this in here. 0.012 kilogram of H2O per kilogram of dry air in the mixture, okay? Okay, let's find the specific volume here. V tilde, that's going to be V tilde evaluated at a temperature of 20 degrees C and a relative humidity of 80%. Let's go back to the psychrometric chart and have a look. See if we can find our relative, our specific volume, V tilde. Okay, so this is our state right here. We know that's our state, the intersection of the 80% and the 20 degrees C. Now, you can see here, it says specific volume right here. Now, notice these charts are kind of nice. The actual angle of the labels tells you what line to use. For example, specific enthalpy, you look at the label here and you take the perpendicular to it. You know lines of constant enthalpy, H tilde, go in this direction. The lines of constant specific volume, you know, go in this direction. See, there's a label right there. You can actually see some numbers here. Here's 0.85. Here's a line of constant. It says, you can't read it because I've drawn a line through it, but it says 0.85. Here's another one, 0.8, 0.75, and 0.9. That has units of cubic meters of the mixture per kilogram of dry air. That is per kilogram of dry air. So make sure you put a dry air there. Okay, so I'm right here. Here's 0.8, here's 0.1, 0.81, 0.82, 0.83, 0.84, and then I have 0.85. I'm right in between 0.84 and 0.85. So I'm going to draw a line here if I can. I'm going to draw a line that is perpendicular. A little bit hard to do, that is perpendicular. So this is 0.8. I'm going to draw a line right here that is perpendicular to this line, if I can. And there we go. So I'm going to write here V tilde approximately equal 0.845. And that's going to have units of cubic meters per kilogram dry air, cubic meters per kilogram dry air. So 0.85. 0.85 is the value I get there, approximately. Halfway between 8.4 and 8.5. You should whip out your copy of the psychrometric chart and follow along. Print copy off. I should have posted a high resolution copy for you. Print it off so you can actually follow what's going on, because that scanner does a terrible job resolving resolving the numbers. So let's see here. This is 0.845. and that is cubic meters per kilogram dry air. I'm going to put approximately equal here. We're kind of eyeballing it, 0.845 cubic meters per kilogram. Okay, so that's the specific volume of the moist air per kilogram of dry air on a kilogram of dry air basis. Let's calculate the enthalpy, specific enthalpy for the moist air per kilogram of dry air. Again, my state is right here. So I am going to put my ruler and pivot on that state. And I'm going to pivot until I get a reading here and here that is the same. Let's see here. That's 50 kilojoules per kilogram. No, it's 55 down here. How about 51? Actually, it looks to me like right about 51. Right about 51. So this says this is 50, 51, 52 kilojoule per kilogram of dry air. And this is 50, 51 right here, kilojoule per kilogram of dry air. Okay, so it looks to me like H tilde is approximately equal to about 51 kilojoules per kilogram dry air. Okay, so the axes here, and here give you specific enthalpy, H tilde. Okay, notice that the axis continues up here. So as soon as we get to 60, it switches over to the y-axis. The angle is maintained. And then as you go up, it switches over to the top x-axis as well. Okay? All right, so H tilde, 51 kilojoules per kilogram of dry air. So H tilde is equal to H tilde evaluated at T equals 20 degrees C and a relative humidity 80%. And I get approximately equal 51 kilojoules in the moist air mixture per kilogram of dry air. So it's per kilogram of dry air in the mixture. Okay, last thing we're supposed to figure out is the temperature. I guess I should put these in here. The last thing we're supposed to figure out is the temperature at which we have a relative humidity of 100%. See, hold on a second. 5 meters cubed per kilogram dry air and 51 kilojoules per kilogram dry air. The last thing we're supposed to find is the temperature, or dry bulb temperature if you like, in which relative humidity would be at 100%. The air would be saturated. That's actually pretty easy to do with the psychrometric chart. Okay, so we know we have a humidity ratio. We know we have a humidity ratio of 0.012 kilogram H2O per kilogram of dry air. Now, as I cool the room down, I'm not injecting any moisture or dry air into the room. I'm just changing the temperature. That means the absolute humidity ratio, omega, is constant. So I'm moving along this horizontal line, constant absolute humidity. So I'm going to start off at my state for the room, and I'm going to cool the room down. I'm going to cool the room down until I get to a relative humidity of 100%. And then I'm going to go down. Going to go down to my temperature axis. And I see that T evaluated at omega 0.012. Relative humidity equals 100% is approximately equal to, let's see, this is 15, this is 16, 17, 18, 19. So it looks like about 16 degrees. Okay, about 16 degrees. 20, so all I got to do is reduce the temperature of the room by 4 degrees, and dew will start to form on any cooler, on the walls, on the ceiling, on the carpet. I try to force the temperature below 16 degrees, dew is going to start forming on the various surfaces in the room. Okay, so I'm going to write here the temperature at which omega equals 0.012 kilograms H2O per kilogram dry air and a relative humidity of 100%. So the air is saturated, is approximately equal to 16 degrees C. Okay? So I'll put 16 degrees C here. By the way, this temperature at which the moist air is saturated with H2O, it can't hold any more. In other words, the partial pressure of the H2O is equal to the saturation pressure of the H2O at that temperature. This is called the dew point. Dew point temp. Dew point temperature. The T temperature at which the air is 100% saturated. Relative humidity of 100% is called the dew point temperature. Okay. Okay, let's make a little bit rigorous here this idea of the dew point temperature. The temperature at which the moist air is saturated with H2O. It can't take any more H2O. It can't absorb any more H2O vapor into the mixture, so it's saturated. Its relative humidity is 100%. So let's say we start off with a room or a container of moist air at state 1. So we have a temperature T1, an absolute humidity or humidity ratio omega 1. And then we have a relative humidity that is less than 100%. So we are not saturated at state 1. Now what I'm going to do is extract heat, cool down the mixture, and I'm going to cool it down until the relative humidity is 100%. So I'm reducing the temperature and therefore reducing Psat. I'm reducing Psat in the moist air. The amount of moist air is constant in this container. I'm not adding any moist air, any dry air. I'm not adding any H2O. I'm not adding any dry air. So omega is the same at state 2 as at state 1. So that means the partial pressure of the H2O stays the same because the amount of H2O in the mixture doesn't change, so its partial pressure remains constant. But the temperature is falling, so that means my saturation pressure for the H2O is also falling. So that's pushing up my relative humidity. So just to remind you here, so the partial pressure of the H2O at state 1 is equal to the partial pressure of the H2O at state 2. Why is that true? Because omega 1 is equal to omega 2 here. I'm not adding any moisture or any dry air, so the absolute humidities are the same. But as temperature goes down, but Psat T1 is greater than Psat T2 because temperature is falling, okay? Because temperature is falling. Temperature 2 is less than T1, okay? And that means, of course, that relative humidity is going up, So Relative humidity at state 2 is greater than state 1. So we're going to reduce the temperature until we get to a saturation point. That temperature T2, so that temperature T2 is called the T dew point. Dew point temperature, usually abbreviated just TDP, dew point temperature. So the temperature at which the air is saturated, the moist air is saturated without changing its composition, just cooling it down, that temperature is called the dew point temperature. It's the temperature at which H2O just starts to condense into a liquid. The air is saturated, so if I try to extract any more heat and reduce the temperature below the dew point temperature, if I try to reduce the temperature below the dew point temperature, H2O will start to liquefy and concentrate and condense on surfaces. So if I try to reduce the temperature below the dew point temperature, I get condensation on surfaces. Let's do an example here. Let's do an example. So we have, let's do a little schematic here. We have a house or a room in a house. So here's our house right here. Here's the roof. And this house has air with the following properties. So we have T equals 25 degrees C. We have the relative humidity of 65%. And what I have here is a cold window. So outside it's cold, and I have a cold window. And the window temperature is 12 degrees C. It's colder than the room temperature. So T window equals 12 degrees C. 12 degrees C, okay? Cold window in a warm room. I want to know what the dew point temperature is for the air in this room. What's the dew point temperature? T dew point. And I want to know whether moisture is condensing on this window. If the window temperature, 12 degrees C, is below the dew point temperature, that means the air near the window is super saturated. Moisture is going to start condensing in droplets on the window and start running down the window. We're going to get condensation on the window if it is super saturated at the window surface at 12 degrees. So we're going to look at the dew point temperature. And if the dew point temperature, if the window temperature is below the dew point temperature, we're going to get condensation. So let's get started here. So T dew point. Well, T dew point is equal to temperature evaluated at omega equals something. We don't know what the absolute humidity is in the room. We're going to find out in a moment. So temperature at which omega equals something, we're going to look at that, and the relative humidity equals 100%. Okay? So let's use a psychometric chart here and figure out what our state is for the air in the room. Let's use our psychometric chart. Okay, so we are at what? We're at a temperature of 25 degrees C and a relative humidity of 65%. Okay, so let's find that state on our psychometric chart. First of all, let's put the 25 degrees in. Oops, that didn't work well. There we go. So this is temperature. T equals 25 degrees C. Okay, so there's our temperature. Now we have 65% relative humidity. 65% relative humidity.
So here we have 100%, 90%, 80%, 70, 60. So 65 is right in between these two curves. A little bit hard to find here, so let's start with the 60. Let's go to the 60. Okay, there's my dry bulb temperature, and the next line up is 70% relative humidity. We're like right in between. So I'm going to put a point halfway between the 70 and the 60% relative humidity. And now I'm going to put a line indicating our absolute humidity. Okay, our line indicating our absolute humidity. So omega is equal to, it's about 0.013, about 0.013, okay? A little bit higher maybe, 0.01, I guess 0135. And that's going to have units of kilograms of H2O per kilogram of dry air, okay? I'm going to write that over here, 0.0135. So omega is equal to omega evaluated at a temperature of 25 degrees C and a relative humidity of 65%. And it's equal to 0.0135 kilograms of H2O per kilogram of dry air. So I'm going to write that right up here, 0.0135 kilograms of H2O per kilogram of dry air. That's the moisture content, absolute moisture content of my air in the house, okay? Now what I'm going to do, I'm going to cool the air. I'm not going to change its composition. I'm not going to change its omega. I'm going to cool the air. I'm going to go along a line of constant omega, constant absolute humidity. So I'm going to start here and I'm going to move over here to 100%. So this is our saturation line. That is omega equals 100% right there. Okay, so I've moved over, a little bit hard to see here. And that is my saturated state. And now I'm going to go down, use a sharper pencil here. I'm going to go down and find my corresponding temperature. Make sure you have this vertical. That looks pretty good. So this is T evaluated at 100%. That doesn't look good. T is 100% relative humidity, and omega equals 0.0135. That's our absolute humidity. And that temperature, let's see here, here's 15, 16, 17, 18. Looks like 18 degrees. So I'm going to put in approximately 18 degrees centigrade. Approximately 18 degrees centigrade, okay? 19, 20, 18 degrees centigrade. So our dew point temperature, T dew point, is approximately 18 degrees C. Approximately 18 degrees C. Dew point temperature. Dew point temperature, 18 degrees C. Okay? Now, the window is at 12 degrees. So T window is less than the dew point temperature. That means the air around the window is colder than the dew point temperature. That means the moisture is going to start condensing on the nearest surface. What's the nearest surface? The pane of glass on the window. So we're going to get condensation. So it's supersaturated near window. super saturated near window. This implies condensation, droplet condensation on window. So condensation of liquid H2O on window. So there's going to be droplets dripping off this window. Liquid water condensate. Liquid water condensate, okay? So, oops, let me write, I guess I didn't finish this. Dew point temperature was 18 degrees C, and we're below that, so we're going to get condensation. Okay. Okay, so far we've done examples where we've been given the relative humidity or the absolute humidity, and certainly we've been given temperatures. Question is, how do you get relative humidity or absolute humidity for a moist air mixture? How do you do it? Is there some sort of device that we can, or procedure we can think of or devise that allows us to easily calculate or determine the relative humidity of some sample of moist air? Well, this brings us to the example of adiabatic saturation. We're going to apply an energy balance to a fairly simple, relatively simple apparatus or device. It's a duct. We're going to feed some H2O into a duct until the air is saturated. So we're going to use this simple device to get a procedure and develop a device that allows us to easily, relatively easily, determine humidity ratio, omega, absolute humidity, and or relative humidity, okay? So first thing I want to do before we get started here is I want to point out that from the psychometric chart, so let's go to the psychometric chart here. I do want to point out, so it's our previous example here. I do want to point out, because this is a two-dimensional plot, it implies that every property here, specific enthalpy, relative humidity, specific volume, temperature, absolute humidity, all of them are a function of two properties. It is a two-dimensional plot. So you give me two properties, I can locate myself on the chart, and then I can determine any other property. So in general, we need two properties to determine other properties, or the state, determine the state and therefore other properties of a mixture. So, note all, so the state, well, let me rephrase here. The state of the mixture can be determined by two properties, and therefore all other properties can be determined by knowing two properties. So the moist air state determined by two properties, properties. An example would be, let's say you know the dry bulb temperature and you know the relative humidity. That puts you on the psychometric chart. So moist air state determined by two properties. For example, it's not always temperature and relative humidity. So I'll put e.g. temperature and relative humidity. Therefore, any other properties, all props are a function of two properties. For example, the specific enthalpy of the mixture might be a function of the dry bulb temperature or temperature T and the relative humidity, and the specific volume of the moist air mixture, again, might be a function of the dry bulb temperature and the relative humidity, okay? That's just something to point out. It's just something to point out. Now, let's use this fact. Let's use this fact on a particular situation, a particular device. We'll apply our energy and our mass balances and derive the governing equation relating various properties. And that will lead us to a device that we can easily construct to calculate or measure or infer the state of a moist air mixture. So let's say I have a device. And this device is a duct. It's going to be an insulated duct. Insulated duct. Okay, so we're going to have an insulated duct. This is our device. So here's the device right here. So here's our duct. Now I have an inlet at location 1, and I have air coming in. I have a certain amount of moist air coming in, and as a result, a certain amount of dry air coming in. Dry air is one component of the moist air. I have a certain temperature, and this is all at state 1. I have a certain temperature T1, and I have a certain relative humidity psi1, okay? Now this is insulated, so there's no heat transfer. But there is a port at the bottom where I can inject liquid H2O. So I can inject m dot H2O liquid. Okay, I can inject H2O liquid at the port. This port here, I'm going to call this location 3. That's location 3. The outlet is location 2. So the air flows in, goes into the port, and there's some liquid here that gets evaporated and humidifies, raises the relative humidity of the air. And at the outlet, I have a temperature T2, and I have a relative humidity equal to 100%. So it is saturated at the outlet, okay? We're adding H2O, and the H2O is evaporating, humidifying the air until it's saturated at the outlet, okay? So my control volume here, here's my control volume. Clearly, this is an open system. Clearly, this is an open system, okay? Now, by the way, a little constraint here. I'm going to constrain the mass flow of the liquid, which eventually evaporates in the duct to humidify the air. I'm going to constrain the temperature here for the inflow of liquid to be equal to the outflow temperature. So I'm going to say here that T3 is equal to T2. I'm going to underline that. The temperature of the injected liquid is equal to the outlet moist air temperature, okay? Now, let's apply the energy balance to this problem. E balance. Okay? So clearly, there's no heat transfer going on because it's adiabatic. It's insulated. So note, this is adiabatic. Adiabatic. There's no work going on. There's no shaft work, no electric work, no boundary work going on. So Q dot minus W dot is equal to dECV dt plus the sum of m dot H plus PE plus KE summed over all outlets minus the same thing summed over all inlets. Okay, so there's our energy balance. No heat transfer, no work. We're going to assume it's steady state as well. This is clearly a steady state problem, okay? So it's adiabatic, steady state. I'm also going to neglect changes in kinetic and potential energy of the moist air flowing in and out of the duct, and the kinetic energy of the H2O being pumped in as well. So the specific kinetic energy and specific potential energies at all inlets and outlets approximately equal to 0. So I can get rid of these potential and kinetic energy terms, okay? Now I have two outlets here. I'm sorry, I have one outlet and two inlets. The outlet is at location 2. So I have m dot for the moist air times H at location 2, okay? By the way, I can rewrite this m dot times H at location 2 in terms of m dot of dry air. I can say this, m dot dry air at location 2 times H tilde at location 2. H tilde is kilojoules in the mixture per kilogram of dry air. So that first term, the summation becomes one term, and it's actually equal to m dot dry air H tilde at location 2, okay? Let's see here, the inlets, I have two inlets. I have one at 1 and one at 3. The one at 1 is, I'm going to write this in terms of m dot dry air. M dot dry air at location 1, H tilde at location 1. Okay, so that's one inlet from port number 1. And then I also have the m dot of the liquid H2O and the specific enthalpy of the liquid H2O. Okay? So let's write what I have. 0 equals m dot dry air at location 2, H tilde at location 2, minus m dot dry air at the inlet, H tilde at the inlet, and then I have minus m dot H2O, and then I have H, and this is for the liquid H2O, and I have H for the liquid H2O, okay? Okay, first thing I'm going to do is I'm going to apply a mass balance for the dry air component and a mass balance for the H2O components through my duct. So let's apply a mass balance. Let's apply a mass balance for my dry air in my duct. So let's do a mass balance just for the dry air component. So mass balance, and we're just going to do the dry air. We'll do that first. Let's see here. Let's write the mass balance for an open system. The change of mass of dry air in my control volume, my duct, with respect to time is equal to the sum of the inlet flows of dry air minus the sum of the outlet flows of dry air. Now it's a steady state problem, so there's no buildup of dry air in my duct. So that's going to 0. I have, well, where's the dry air coming in? And where's the dry air going out in the dry air component? So I have moist air flowing in on the left, some of which is dry air. So I have m dot dry air 1, and I have moist air leaving on the right, some of which is dry air. So I have an m dot dry air on the right. So there is a m dot and an m dot dry air on the right flowing out at location 2, okay? So I have an inlet, I have one inlet and one outlet for the dry air. By the way, no dry air comes through port number 3. It's only H2O on port number 3. It's not a mixture of H2O and dry air. It's only H2O on port number 3. So the inlet is m dot dry air at location 1, and the outlet is, there's only one, dry air at location 2. So this means 0 equals m dot dry air at location 1 minus m dot dry air at location 2, and this implies m dot dry air at location 1 is equal to m dot dry air at the outlet, location 2, or if you like, since it's all the same, I am just going to call it m dot dry air. Whatever that is, it's the same on the left as on the right, okay? So all these m dot dry airs become a single m dot dry air, a single m dot dry air, because it's the same on the left and the right. I'm not adding any dry air anywhere to my duct, okay? Now let's do an H2O balance. Let's do the H2O balance. Let's do an H2O balance, the water component, liquid and vapor. Okay, so same thing here. The time rate of change of H2O within my control volume is equal to the sum of the inflows of H2O minus the sum of the outflow of H2O. Okay, let's go back to our diagram here and figure out where the inlet and outlet flows are. H2O is flowing in on the left because it's moist air. I've got dry air, I've got moisture in there too. So I have an m dot H2O. Maybe I'll add it here. So I also have an m dot H2O at 1. And I also have an m dot H2O. It's moist air flowing out. So there's an m dot H2O out as well, okay? So I have an inlet, one inlet here where H2O is flowing in. I also have another inlet here. It's my m dot liquid water. So I got m dot H2O at the inlet, m dot liquid H2O at this inlet, and I have one outlet, m dot H2O at the exit or location 2. So plug in, 2 inlets, 1 outlets. So I have m dot H2O at location 1 plus m dot liquid H2O minus m dot H2O at the outlet. And of course, we're in steady state, so this is 0 right here, okay? So I get 0 is equal to m dot H2O at the inlet plus m dot liquid H2O minus m dot H2O at the outlet, which is location 2, okay? Now I'm going to divide this entire equation by m dot dry air. I'm going to divide the entire equation by m dot dry air. Okay, it's all equal to 0, so I can divide it by anything I want. What is m dot H2O at location 1 divided by m dot dry air? That is the humidity ratio. This is omega 1. Omega 1 is the mass of H2O in the mixture, moist air mixture, divided by the mass of the dry air. This is dots here. It doesn't matter that it's dots. It's just a flow rate. The time the dot cancels out, okay? And this one here, m dot H2O at location 2 divided by m dot dry air, that is omega 2. So what have I got here? So I have omega 1 plus m dot liquid, liquid H2O minus omega 2, and all of that equals 0. Okay? So let's solve for m dot liquid. Oops. M dot dry air. Forgot the m dot dry air. Let's solve for m dot liquid. M dot liquid H2O is equal to m dot dry air times omega out minus omega in. Omega 2 minus omega 1. Okay? Very important equation right there. I'm going to substitute this into my energy balance. So this m dot liquid H2O is m dot dry air times omega 2 minus omega 1. Okay? So let's write what we got here. 0 equals, I'll tell you what, well, okay, m dot dry air, H tilde 2 minus m dot dry air, H tilde 1 minus m dot dry air, omega 2 minus omega 1, H of the liquid H2O. Okay? Notice I have m dot dry air in every term. M dot dry air is in every term. And let's write what I got left over. I have 0 equals H tilde 2 minus H tilde 1 minus omega 2 minus omega 1, H of the liquid H2O. Okay, so that's the energy balance and mass balance included. Essentially, it's my governing equation for my adiabatic duct, where the exit is saturated. I'm injecting H2O until the exit is at a saturated state, okay? Now, I'm going to point something out here. I'm going to rewrite this equation. I'm going to show the dependency on temperature and relative humidity for every one of these terms. In other words, recall, H tilde is a function of temperature and relative humidity, two properties. Omega is a function of temperature and relative humidity, for example, okay? And H for the liquid, so this is a liquid, supercooled liquid for sure, probably being pumped in. So H for the liquid, that is a function of temperature pretty much alone. It's also a function of pressure because it's got the V times VP term in there, but we're at 1 atmosphere. So let's say this thing is at 1 atmosphere. The pressure here is 1 atmosphere. The pressure doesn't change. So the dependence of enthalpy on pressure goes away for this particular situation. It's also an isobaric situation. So H for the liquid H2O is also a function of temperature, okay? So let's rewrite this equation, and I'm going to include the dependencies in here on temperature and relative humidity. 0 equals H tilde T2 relative humidity 2 minus H tilde T1 relative humidity 1 minus omega 2, which is a function of T2 and relative humidity 2, minus omega T1 relative humidity 1. And then I've got H of the liquid H2O, which is a function of temperature, and my temperature for the liquid H2O is T3. Now, let me substitute a few values here. The relative humidity at location 2 is 100%. Okay, 100%. Let's say I know temperature T1. Let's say I know the temperature T1. And let's also say I know temperature T2. So let's say T1 and T2 are known. I simply measure them with a thermometer. Okay? So let's say I know T1 and T2. I know these temperatures. I know all these temperatures. This is one equation. One equation with one unknown. I know all the temperatures. I know the relative humidity at the exit, which is 100%. So this is one equation and one unknown. One unknown. And my one unknown is the relative humidity at the inlet. That means if I can build this device and I can measure the inlet and outlet temperatures, that's all I need to do in theory to find the inlet relative humidity. If I just know the inlet and outlet temperatures, I can find the inlet relative humidity if I can build this device. Fairly simple application of the energy balance to get the relationship. Okay, let me show you a simple version of this device. Very simple version of this device. I guess I'll have to go over here. Very simple. It's so simple you won't believe it. So we're going to take two thermometers. One is a regular thermometer, nice clean thermometer. So we're going to take our thermometer here. Thermometer, so I'm measuring a temperature T, and this is the air temperature, and it's also called the dry bulb temperature. TB, T dry bulb, DB, dry bulb temperature. That's not the way I want to write this. Dry bulb temperature. So it's measuring the temperature T, or T dry bulb, just the plain old temperature, just plain old temperature. And right next to it, and this dry bulb is sitting in moist air. Moist air, it's just sitting in moist air, okay? And then we have another thermometer. And this one is covered in saturated, moist, a cotton gauze, a moist cotton gauze or cotton wool of H2O. Saturated cotton with H2O. So it's liquid water impregnated cotton wool. The temperature measured here is called the wet bulb temperature, TWB, which is wet bulb temperature. So the air is flowing over this. It's cooling down because we're evaporating some of this H2O in the cotton gauze. We end up with saturated moist air. In other words, relative humidity is 100%, trailing off of this wet thermometer, wet bulb thermometer. And we have reproduced the duct. This is equivalent to the duct, where we are pumping in H2O. T2, T1. In this case, T1 is the dry bulb temp. That's what you're measuring here. And T2 is the saturated or wet bulb temp. Or TWB, or T dry bulb. DB or WB, wet bulb, dry bulb. Very simple device for calculating relative humidity. Let me show you some pictures here. Let me see if I can find some pictures for you. Here's one. Let's do a little share here. There we go. So here's one. Actually, I want to share the screen. Sorry about that. Let's just share the screen. There we go. So dry, wet. Here we have the regular thermometer with the scale. So that's just a plain old thermometer. That's reading the temperature in the room or in the moist air. That's our dry bulb temperature. And this here is our wet bulb. Notice there's a little tank of water here, and there's a wick, a cotton wick that is clamped or surrounds the bulb of the wet bulb thermometer. See, it says wet up here. So knowing the dry bulb temperature and the wet bulb temperature, I can extract out any properties for the mixture, any properties. Let's go back to our psychometric chart. Psychometric chart. Remember, dry bulb temperature, that's here, that's on the x-axis, that's the dry bulb temperature. Then it says wet bulb temperature. These lines here, 10, 20, 25, 30, these big bold lines right here, these are constant wet bulb temperatures. Constant wet bulb temperatures. Okay? And in this case, you're using a sling hygrometer, this device that calculates uses the dry and wet bulb temperature is actually called a hygrometer. So let me write this up for you. So this guy is called a hygrometer, and you can buy them. They're not very expensive. So this is a hygrometer. Hygrometer. It uses a wet and a dry bulb temperature, along with the psychometric chart, to give you the state and therefore all properties of the mixture. The flames, this right here, and the one I just showed you, this is a very slow, so let me go back here. This thing, you just put it on the outside of your house, and it gets to a steady state more or less. But it takes a while to get to a steady state. Temperature is changing very quickly, or you move it into a different room. It's not accurate for a little while. So you can actually use what are called sling hygrometers. Let me see if I can find one for you. Do a search here. This is not good. So let's do a hygrometer. Sling hygrometer. Let's see if we can see a picture of a sling hygrometer. Ah, there we go. Here's one. Let me see if there are some images. Yeah, so what you do is, here's one. Wet bulb, dry bulb. This is a handle. You take this thing and you sling it around, you twirl it around like a whip. And air flows very rapidly through the ports here, quickly giving you a steady state wet and dry bulb temperature. Notice that our energy balance was not a function of m dot dry air. So it doesn't matter how fast the air flows through here, you're still going to get the same wet and dry bulb temperatures. M dot dry air was not in our final energy balance, so it doesn't matter how fast you swing it around, you're still going to eventually get, quickly or slowly, you're still going to get the same wet and dry bulb temperatures, okay? Okay, ladies and gentlemen, that was a pretty long lecture there. I think we're done. Take care.